It is my great, great, great pleasure to introduce Professor, and I'm not going to say it right, Krste Asanovic. And he teaches here, of course. Very interested in architecture, VLSI, scaling efficiency. And I apologize, this probably isn't the best introduction you'll ever get. But the really important thing about this wonderful teacher is that, well, two things. One is he got his PhD here, where people are taught to think more clearly than many other places about these things. And because of that, when he went to teach at MIT after a while, he came back here because he'd been taught to think more clearly about. So, without further ado, here he is.
Right, this microphone is a little low for me, so I'll try and shout so you can hear me. I'm really delighted to be here today. Honor Dave. So actually, just reminding myself, I first got to know Dave as a grad student in his CS 252 class back in 1990. And I saw Ethan Miller was around, and he was a TA. And one of the great things about Berkeley classes, you do class projects, and some of those lead to papers. And lo and behold, from that class, I did a paper on the stall cache, which, as you all know, took over the world by storm. The most important thing about that was that Klaus Schauser, who was my project partner there, we both got to go to Kauai. So that was a real success, early success in my grad student career. But then actually what I was working on during my grad school career was this really obscure topic, which was building fixed point vector processors to accelerate neural network training. As we all know, this has gone absolutely nowhere. No one actually cares about that at all these days. But this is one of those things where if I just stuck at it for 25 years, I would be a hot topic again. So thanks, Dave, for the advice. So, thanks to Dave, a lot of good advice from Dave. I had a great career here as a grad student, and I got involved with the IRON project just as I was finishing up my degree. And I have to say that Dave was on my thesis committee, and he gave me the most feedback, the clearest comments on my thesis of anybody else on my committee. So thank you, Dave. Really appreciate that. He also gave me a lot of great advice over the years. I went to MIT, did a lot of stuff there. I really, as Dave pointed out, you know, the last few times you shovel your car out of the snow at Logan Airport, and Bill will appreciate this, you know, you're sitting there thinking, I'm a smart guy, why am I living in Boston? Right? So luckily I managed to come back to the Bay Area, and you know, on my sabbatical year where I was trying things out, we got the PAR Lab started, a whole bunch of meetings, this thing Dave was talking about, getting the faculty together, throwing around a lot of ideas, and that resulted in PAR Lab, and we had a lot of fun. That was a great success. And then that followed on with the Aspire Lab. So Dave's a great teacher. All stages through my career has given me great advice and guidance and support, so thank you, Dave. I really appreciate it. Okay, but the topic of today's talk, risk, one of the things Dave's very well known for. And we're talking about risk 5 today and why instruction sets want to be free. So, you know, why do instruction set architectures matter? Isn't this old stuff? It's all hidden under 57 layers of virtualization. Who cares about the ISA? Well, the reason it matters, I'll just ask you a few rhetorical questions. Why can't Intel sell mobile chips? It's because of the ISA, right? So almost all of them are based on ARM v7, v8 ISA. There's maybe a few other technical failings at Intel, but predominantly, they cannot shove x86 down the throats of people who are happily using the ARM ISA. So look, things look good for ARM, except why can't ARM sell servers, right? Because they're all using the AMD ISA that Intel fabricates and manufactures in their chips. Another side story, why is it an AMD ISA that's in all these servers? Because Intel wanted to monopolize the entire market and force people to go to Itanium for their 64-bit architecture. Thankfully, that failed. That effort failed, and people had more compatibility with the previous generation. Or another question you might ask is, how can IBM still sell mainframes, right? So, you know, the IBM 360 is the oldest surviving ISA, 50 plus years and still going strong. They're making billions of dollars of revenue profit on that line of machines to this day. So the ISA is really, it's the most important interface in a computer system because it's where software meets hardware, right? And it has this big impact in our industry. Now, what you may not realize, people think, oh, that this chip is an ARM chip, this chip is an x86 chip. But almost every chip today has many, many ISAs on there. And I've talked to people, and it's somewhere around 15 or 16 is not uncommon. 15 or 16 different instruction sets on a single SoC. Why are there so many? Well, apart from the application processors we all kind of know about, there is graphics processors, there's image processors, radio, audio, security, power management, lots of other random microcontrollers they throw on there. So why don't they just use the standard ISAs? Well, if you go look at the industry standard ISAs, they're just way too big. Clunky, cumbersome, not well designed. And so a lot of places, they'll also buy IP in from other sources, but they'll also develop these in-house. They'll have their own private ISA they just use on their own product. And this looks like a really good idea the first time they do it compared to licensing from somebody else. Oh, this is really cheap. I took Dave's class. I know how to build a RISC pipeline. You know, I took the compilers class at Berkeley. I know how to port GCC. It wouldn't take very long. And it doesn't take too long to get something working. But then the trouble is your chip is successful and the manager wants to do a second one, right? And then you have to support that software stack of that plus all the other ISAs that are on that chip. And that becomes untenable after a while. So many, many ISAs on a chip causing a large software maintenance cost. And remember, most of these ISAs are on things that the software developer, as you think of them, never sees. They're just hidden away inside the chip. So do we really need all these different ISAs? And do they have to be proprietary? Why are they all proprietary? What if there was one free and open ISA that anybody could use for anything? And that's basically the premise of RISC-V, right? Now, open software standards and almost everywhere else in the industry, they work really well. You have networking, Ethernet, TCP/IP. Imagine if we had IBM Net, DECnet. Oh, we used to have that, right? All gone, right? Imagine operating systems. Imagine we have the IBM OS, blah, blah, blah. Oh, that's gone, right? Linux. Everybody's using POSIX. You can even run POSIX on Windows 10 now, right? A bash shell on Windows 10. Okay, so open standards are great, but down at the architecture level, no. You have proprietary ISAs, x86 and ARM, right? So why don't we have an open standard for this most important interface in the computing industry, right? And it's not like these ISA designs, the standards are any good. They're dismal. They're really bad, right? Dave would give them an F, right? Why did you do that, right? So terrible, terrible designs, but those are the industry standard for the most important interface in the computing system stack. Now, we're not the first people to think about doing an open ISA. There's been several others. To this credit, Spark, which was inspired by the Berkeley work on RISC machines, for version 8, they open sourced this, made an IEEE standard. Not open sourced it, but made the specification open. It was an IEEE standard. And a few people actually offered open source cores. We used it in our projects. But now the ISA is now owned by Oracle, and future evolution is, Larry's business, right? So that's over there. Also, Spark is a little bit technically deficient. Sorry, Dave, but the register windows, every project I've ever done with register windows has caused problems, either in the hardware or the software or somewhere else. Interestingly, another big effort was OpenRISC, who did an open source core implementation. And what this was a bunch of Slovenian undergraduates who were inspired by Dave's book and Dave and John's book, and they took the DLX architecture and basically typed it into Verilog, and that was this OpenRISC core. And that was actually fairly widely used, and this is one of the things we looked at, but looking at it, we realized that for one thing, we wanted to do 64 bits, and this thing wasn't 64-bit. And the other thing was they were really stuck in 1950s architecture in designing this ISA. They really were thinking of the implementation was a thing that people would program, and they hadn't got to the level of 1960s architecture. People realized you could separate the instruction set from the implementation. So these earlier efforts didn't really meet the need of building a free and universal ISA. So for universal ISA, what are the requirements? One thing, you're not going to rewrite all the software in the world, right? So all those great ideas you might have about this is the world's best instruction set architecture, it just doesn't support C. That's not going to work. So it has to support all existing software stacks and operating systems, right? Another key thing is it has to be a real hardware ISA, not a virtual machine or ANDEF. That is, every problem in computer science can be solved with one level of indirection. It's just somebody else's problem to actually follow that link to implement the indirection, right? So even if you had, say, the JVM as a portable standard, that was a great success, right, making that portable. You have to map it down to the native ISA of the thing you're building. You actually have to build hardware that has an instruction set. And that mapping is a very expensive thing to get right. So you see, like, ARM still has troubles having a competitive JVM after all this time, right? It's hard work making those translation layers work. And the other thing is, that's all the virtual machine technology is fine to have. It doesn't remove the need to have a real native hardware ISA that everybody can implement, right? To reuse all that technology. We're really interested in all kinds of systems, from the tiniest microcontroller all the way up to the largest supercomputer. And all implementation technologies, whether it's an FPGA soft core or hardened to an ASIC or a full custom design, asynchronous future device technologies, something that isn't tied to any given implementation technology. And it should be good for all microarchitecture styles. So this thing about separating the architecture from the implementation, in order, decoupled, out of order, sequential, superscalar, it should work well for any of those categories of microarchitecture. We were starting this as part of a research project where we're focusing on this coming wave, the end of Moore's law, the need for specialization. So we were really looking at an ISA that would support adding specialized extensions to support these applications well, things like the neural net accelerators, for example. Now, another big feature we think is really important in universal ISA is that it doesn't change, right? So, it's stable, it doesn't disappear, it doesn't modify, it doesn't get modified, it doesn't go away. One big problem with commercial ISA is they disappear. For example, when DEC went down, they took two important ISAs with them, VAX and Alpha. And no matter what you wanted to do, you could not, as an outsider, keep those ISAs alive because of the IP entanglements, right? So you want to separate your investment in software, which is the big thing, from the business fortunes of the hardware companies, which is a pretty capricious thing, right? So you want something that's stable, not changing, not disappearing. And for our ISA design, we kind of froze it and said we're never gonna add instructions to this. It's just done. Just leave it alone. Go work on more important things in the rest of the stack. So let's talk about where this came from, the origin story. So back in 2010, we'd done many projects using different ISAs, MIPS, Spark, x86, and every so often you kind of reset and say, this was during PowerLab days, what are we going to use as the ISA for our next set of projects? So we did the analysis, and it's pretty clear the obvious choices were x86 and ARM. They were the dominant in the server and the mobile space. So you take a look at ARM, and it's just clearly impossible, right? This thing is just too complex, IP issues. So I do occasionally have this fantasy about implementing an x86, right? Occasionally I just sit down and think, wouldn't it be fun to just go build one of those? Can't be too hard. Then I crack open the manual, right? And the first opcode you see is AAA, right? So what's AAA, right? It's ASCII adjust after addition, right? So this is obviously an important instruction. It's right there at the front. So what does this instruction do? Well, it has an implicit source and destination AL. If the low nibble is greater than 9 decimal, or the auxiliary carry flag is set, then add 6 to the low nibble, discard the overflow, increment the high byte, and set the carry flag and auxiliary flag, okay? Otherwise, just clear the flags. This is obviously a very important instruction because it's given a single byte encoding, right? So you look at this and you say, no way in hell am I touching this, right? So x86 was impossible, how about ARM? So we looked at ARM, that's a RISC machine. The R in ARM stands for RISC, and they were inspired by reading the Berkeley papers from Dave's group, right? At the time we looked at it, I would describe this as mostly impossible, to paraphrase Doug Adams, right? This is, they didn't have 64-bit at the time we started. It's very complicated. It really wasn't a RISC. I think Dave would have given these guys a D-, right? This is kind of a RISC, but not really. And also the IP issues are even worse. So the shortest time in the universe isn't between the New York cabbie behind you seeing the light turn green and honking his horn. It's between you putting up an open source ARM RTL on the web and getting a letter from an ARM lawyer, right? So terrible IP issues. So back in 2010, we started this 3-month summer project to do a clean slate ISA, just build what we actually wanted to build. I'll call out to Andrew Waterman and Yunsub Lee, who are the 2 principal grad students on this. A bunch of other people contributed, along with Dave and myself. They're the main drivers behind this ISA design. So we started this 3-month project in the summer. It's plenty, we'll just get it done by the end of the summer. 4 years later, we actually released the frozen base spec. Now, it wasn't like we just sat in a room and pontificated about instruction set design. Along the way, we did several tape outs, several iterations of this ISA, ported the compilers, changed things around, played with it a lot, and a few research publications also came out of this. So we were working on it quite hard over this period. Now, a curious thing happened as we were working on this. We started getting these random emails from people saying things like, why did you change the spec? And we were like, well, who are you? And why do you care? And what had been happening was outsiders have been seeing this stuff there and been pulling it from our website and using it in their own projects. So we started thinking, oh, maybe there's a need for this outside of Berkeley. Maybe people actually want to have a sensible ISA they can use in their projects. So then we decided to do a more concrete push to actually get this out there. And that's resulted in this RISC-V effort. So people often ask me about the name. So why RISC-V? Some people say, why isn't it RISC-V? If it was RISC-V, then the other ones would have been RISC-I, RISC-II. It's a Roman numeral, you pronounce it 5, right? So RISC-V. Well, we went back and Dave, I think one thing he does regret is he didn't stick with the RISC branding through the other projects, right? So we fixed that for him, later. So his RISC-1, very famous chip, RISC-2, SAW, which Dave here was the leader on, small taconic RISC. We kind of posthumously renamed this. This was actually RISC-3. SPUR, which many of you worked on in the audience, this is RISC-4, and now here's RISC-5. This is the first tape out we did of a RISC-5 chip. So we wanted to keep that legacy. And also, if you look at the instruction set encoding, there's features in there that actually we saw in SPUR, and there is a family resemblance in the instruction set encoding. People say, oh, this looks like a random commercial MIPS or RISC instruction set, and you look at it and goes, no, it looks like the Berkeley ones. They came first with this stuff. So what's different about RISC-5? It's simple. So it's far smaller than the other commercial instruction sets. It's a clean slate design, really separated user from privileged ISA details. We also separated microarchitecture and technology-dependent things out of the ISA. A lot of the commercial ISAs have made big mistakes in these areas. It's a modular ISA, so it's designed that there's this very small base that you can use if, for example, you want to build one of those accelerators and you want to add all the stuff on the side without beefing it up with stuff you're not going to use. And there's a lot of standard extensions on the side as well. And it really was designed for extensibility and specialization. This coming era, we're going to have many weird and wonderful computer architectures designed, but they're all going to have to actually run software. So you need a stable base which can run most of the software, plus a facility for adding the specialized engines that are going to give you the energy efficiency you need for these new applications. Like I said, it's very stable. The user level base ISA we froze when we announced it. I think that was a very smart move on our part. And all the additions to this will be done as optional extensions. So the trick is, don't have version 8, version 8.1, version 8.2, version 8.3 to pick some random numbers. Instead, do the additions as optional extensions, because the base is enough to run all software pretty well. So I'll just quickly go through this. Don't want to dive too much into details, but in RISC-5, there are 3 address widths, 32-bit, 64-bit, and 128-bit. And there's 2 variants of the 32-bit, one with fewer registers than the other, just for very small microcontrollers. And for the basic integer instruction set, there's less than 50 instructions needed to implement those bases, and that's enough to run all the modern software stack, GCC with dynamic linking, position-independent code, and an operating system. Right? So very few instructions are mandatorily needed in the base to get things off the ground, and if you're building an accelerator, you can just start with that, have a full compiler toolchain, everything ready to go, and add your stuff on the side. Keep things very lean. On top of that, there's a bunch of standard extensions for integer multiply divide, atomics, single precision, double precision, floating point. And so put these all together, you get a relatively standard ISA for software development on, say, a Unix platform. And all of these, the base instructions, we designed them to fit into a standard RISC instruction format. We took a bit of care with this. People who've implemented this will appreciate what we did. At the surface, it just looks like any other RISC. We made sure the source registers and the destination registers are in the same place. They don't move around. And the immediates are all sign extended from the same point in the instruction word. So very simple standard RISC encoding format. So in adding to this, one of the extensions we looked at was the atomic operations on top of RISC-5, the A extension. And there's 2 classes here, atomic memory ops, fetch and op, as well as load reserve store conditional. Now when we were doing this, and this is part of one thing we did here is put out drafts to the community. There's a bunch of people using this, and they gave us a lot of feedback. And during that course of that process, we kind of realized the language community seemed to have got their act together a little bit in terms of memory modeling languages. So we wanted to make sure to support those well in the architecture. So the AMOs can be annotated with 2 bits. They give you basically release consistency. There's an acquire bit and a release bit that orders those AMOs relative to other AMOs. So we thought pretty hard about supporting the languages. I believe ARM added this later on into 8.1 or something of the ARM as well. So one other thing we decided from the get-go is compressed instructions are very important and extensions are very important. So you need a lot of opcode space. So we want to make sure that the classic RISC philosophy was everything was a fixed size. We want to go back to Cray, who realized that 16-bit parcels are actually a pretty good unit for instruction bits. So the RISC-5 encoding, if the bottom 2 bits of the word are 1-1, it's a 32-bit instruction or longer. If they're not 1-1, then it's a 16-bit instruction. So now the compressed instructions here just slide into the encoding. They're not like in the other ISAs, they didn't leave enough room in their base, so they have to jump to a different instruction set when they want it to be compressed. Here the compressed extension is just 16-bit words that get mixed in with the regular 32-bit words of your regular 30-bit encoding. And we also support way up, many bits long instruction encoding as well using this trick. The only real penalty we pay for this is that branches and jumps are reduced in range by 1 bit, but we felt that was a great trade-off to get this flexibility. So the compressed instruction set extension, compressed code is really important for low-end embedded, where you're paying for the flash memory or to hold your code. It's also very important for high-end commercial workloads, where often instruction fetch, instruction caching is a dominant issue. So we added a bunch of compressed instructions. We took a philosophy of making this a very simple extension to have in hardware, and the principle was every single compressed instruction expanded to exactly one of the regular size instructions, right? And this meant that the whole decoder, the decompressor, takes around 700 gates, which is a tiny amount in modern technology. As I mentioned before, all the original instructions are available. They just now can be aligned on a 16-bit boundary. So this seems to work pretty well, and you get about a 25 to 30% saving in code size. And comparing to other architectures, this is comparing against the x-axis of different ISAs. The y-axis is the size relative to our compressed instruction set. So you see that in the 32-bit address space versions, we're comparable to ARM Thumb2, a lot smaller than all the other ISAs out there, including x86. In the 64-bit address space, ARM doesn't have a compressed encoding, so we're actually significantly smaller than any of the other ISAs in the 64-bit address space. And I could do a chart for the 128-bit, but it'd be very boring because we'd just be the only ones present in the 120-bit address space, right? So actually, the 128-bit we added as kind of a joke in the first version of the ISA manual because we felt, well, the one thing we learned, there's a classic quote about the only mistake an ISA can't recover from is not having enough address bits. And so we made sure that wouldn't be a problem. But as we started talking to people working in data centers, we heard the talk from Amin and other people earlier on today, you have very large solid-state memories, and those are getting to be tens of petabytes or more storage space. And when you get to 10 to 100 petabytes, you start getting to 57 odd bits, and you don't want to densely pack an address space. So there may be a need for more than 64 bits of address space if you're going to have these richly connected data center clusters with lots of non-volatile solid-state memory, right? So 120 bits may be coming sooner than I would have thought. So another piece of the ISA encoding we added was the vector instruction. So I've been, ever since those days building fixed-point engines for neural net training, I've been a big fan of vector machines. And so RISC-V will have a vector-style extension a la Cray, as opposed to PAC-SIMD or other stuff you have in the other ISAs. I'll just run through this quickly. Just to say, this is more like the standard Cray-style model, which is going to lead to a massive reduction in the number of instructions you have to implement, because we don't need a different instruction for every width of vectored register, like the other ISAs have done. So we've also engineered all the privileged architecture to be very clean and to really emphasize a clean split between the layers in the stack. So for example, the supervisor code never actually touches the machine. It's kind of always running virtualized in RISC-V, and there's a low-level machine mode that provides security and isolates the physical hardware from the OS. Right? So we thought really hard about this at the privilege level. So Dave is really great at building green cards. So he managed to squeeze the entire instruction set onto one PowerPoint slide. And you can almost read it. I can read it from here. So this is the 32-bit. We add multiply, divide, the privileged instructions, atomic instructions, the single, double, quad precision floating point, the compressed instructions. And this is a few more are needed for 64-bit and 128-bit extensions. And that's basically it. And this all fits on a green card. And I think this is due to Mark Hill, but you can tell it's a RISC because the manual doesn't need a staple, right? Right. So now, it's really simple. And the thing about, you go talk to people in industry, and it's like, well, simplicity breeds contempt. How could this puny little academic thing compete with the industry monsters? The answer is really well, actually. And I can't disclose anything, but I've spoken to several different big companies who've ran internal evaluations against the commercial ISAs, and are surprised how well RISC-V does, and actually beats a lot of the other ISAs on most important metrics. So Cray and the RISC advocates, Dave, John, other people, they were right. You only really need that simple stuff, because the simple stuff happens all the time, right? And keeping it simple has many advantages. Helps with teaching, what professors do, learning, what students and engineers do, area, energy, quality, verification, security. It's keeping it simple, one of Dave's big lessons. He keeps telling people, it really helps a lot. So Berkeley, we built a lot of chips with this. So one difference with the earlier RISC projects, we didn't just build one chip and that was it. We built an architecture and used that in many projects. So we built 12 RISC-V chips, I think, so far, in 28 nanometer, 45 nanometer technology. As I said, this helped us prove out the design and make sure it was working okay. The cores we built are pretty competitive with industry cores. I urge you to look at the proceedings of the RISC-V workshop to find out more. And just throw up a couple of random things we built at Berkeley. One is a single chip vector processor with integrated silicon photonics. This might be a solution to the networking problem in the data center. So there's dual RISC-V cache coherent processors with vector accelerators. These are the photonic IOs. And this actually appeared in Nature as the first single chip microprocessor that communicates directly with light. So I urge you to go read that. We also worked on DC-DC converters. Very efficient, operating down to 0.45 volts and getting computer efficiencies, actually running code, double precision, floating point up to about 34 to 50 gigaflops per watt, which is really ahead of the art. So closing out here, so RISC-V started at Berkeley. We've been pushing it out to the world. In order to make it last longer, I created this foundation, the RISC-V Foundation. We're sort of looking for members. It's a 501c6. The principles are this whole stuff is free and open to anybody to use anywhere. The only constraint is if you want to use the RISC-V trademark, you have to be a member of the foundation and pass the compatibility suites. That's to avoid fragmentation. We've done really well with our membership. So we've, in the RISC-V workshop in January, we had 16 members. We're up to about 30 now or so, not all of them on the website, but Google, Oracle, Hewlett-Packard, Western Digital, Mellanox, Microsemi, IDT, a whole bunch of companies. There's a bunch more lined up who will be joining. Have joined this effort, and this is our little startup, Sci5. Come see me if you're interested in Sci5. To learn more about RISC-V, go to the website, risc5.org. Just to give you some idea of the uptake, this is a picture from the third RISC-V workshop in January that was held at Oracle. Sold out, a lot of companies. Google announced that Core Boot doesn't commit unless RISC-V port commits. HPE is working on UFI for RISC-V. Jan Gray managed to put 400 RISC-V cores on one FPGA and get an aggregate performance of more than 1 MIPS per LUT, which I thought was pretty incredible. The next workshop is July at MIT, so please go to the website, register, show up if you can. I think you'll find it exciting. So one other thing happened, the Global Semiconductor Alliance put out a report sponsored by Rambus, and one of the chapters in there talks about how open source may save the hardware industry. And one thing they point out was RISC-V as being the Linux of microprocessors. Okay, so to summarize, why RISC-V? Well, it's a free and open architecture, no proprietary lock-in. It's much simpler than others. This really helps with verification security issues. It's ready extensible, better area power performance than the other guys. And you can use it as the base ISA for every core and SoC. So our modest goal at this point is basically become the last ISA. This is the industry standard ISA for all computing devices. Right, that's it. Done. Thank you.
Thank you so much. And I have to say, I only wish the users of programming languages understood the virtues of simplicity as well as the people who develop and use the ISAs here. So let's take a few questions for Professor Asanovic. Are there any hands? It's hard to see with the lights. Speak up if you have a question. There's one.
How will the industry, excuse me, how will the industry create vendor lock-in if everyone adopts your processor?
Well, that's the great thing they can't, right?
Oh, you need the mic.
That's the kind of the whole point. So most of the value is in the software, right? So I think people confuse it. Open source hardware is really about the software. So people should realize.
Go ahead, yeah.
So could you comment on the virtual memory architecture as well?
I could, it'd take a while. 4 kilobyte pages, lots of them. And we can talk more offline, I think.
Okay, one more question? Okay.
All right.
Thanks again.